Because it's so like you.
Yes.
Everything revolves around me.
No, it's not. It has nothing to do with me. Look who is there.
Yeah, and then your name's all fake.
No, my name is, I'm a speaker. I'm supposed to be somewhere. I'm at the bottom.
You're so easy to tease.
I'm just at the bottom. What else, guys, do you want?
You're so easy to tease.
What?
You're so easy to tease.
Yeah, I know. And even she's been teasing me.
Yeah, because she told me you made your own flyer and it made me laugh.
Whatever you guys do.
Angel was cracking up. Because it is so like you. And at first Angel goes, "Who is that?" And I was like, "It's Albert Einstein."
No, I am not.
It is very much like you.
It's not.
Yeah. Don't look at me. I'm not to blame on anything.
No, I don't know. I'm appreciating what it is.
Maybe the new dean doesn't realize. I don't know. I can't say. I can't speak for other people. I'm sorry.
It's okay. I may finish on time. Who knows? I will try though, should I?
Yeah, he's contagious.
We'll see.
Dr. Weiss is all isolated. Are you nervous?
What?
Are you nervous?
Oh,
I know. I'm just teasing you. So,
I hope I don't start yelling. That's a good sign.
this morning I threw up and I got it on my shirt, but I got it out. You can't even see it.
Oh,
That's why Stacey's like, "Are we all getting sick?" I think mine's allergy. I don't think I'm getting sick. It's weird that there's just this random chair.
yeah.
Okay, let's start. This week, hello. Let's get started. It's 4 o'clock. Otherwise, we're going to go at 5. So this week we have one of our own, Dr. Musielak talking about 100 years of general relativity.
Thank you very much, Hara, for this introduction.
Very short. Yeah, all the time.
Yeah, sure. Thank you very much for all of you for to come to this talk, because this talk, it's supposed to be a tribute to Einstein's general theory of relativity and to Einstein by himself, a person who really produced it. What I would like to do in this talk will have a few different topics which would be separated. First, there will be brief introduction to history of general relativity with some unfolding drama which underlines the development. But nevertheless, I don't want you to panic. My talk will not be rated R. Ooh. It's still PG-13, okay? So we can manage, okay? We can manage. But there will be something. And then I will talk about first predictions and limitations with very specific applications. And after that, I will say something about some challenges which are ahead of us, and hopefully I will have a few minutes to get to our own research on general relativity. So the starting point obviously should be special theory of relativity, which Einstein published in one of the 5 papers which changed the face of physics in 1905. And special theory of relativity, I just basically said here what is about, namely saying that it is about the fact that all inertial observers that all inertial observers are treated equally, and the fact that speed of light is the same for all of them requires that space and time are relative, and they actually are mixed together, which Einstein presented this very well in his paper. However, he never got that point that when they should be put together actually and mixed together, which was done by somebody else. I will say a few words about this. Now, one thing that Einstein theory cannot describe is these two very happy guys who are just simply going on a roller coaster because they are accelerating. And theory is purely and exclusively about inertial systems. So what it is actually, what kind of space-time underlines Einstein's special theory of relativity? The space-time is the space-time continuum, which was actually brought to Einstein's attention for the first time in year 1908, and Einstein didn't like it. Einstein was known for the fact that if the idea came from somebody else, he first didn't like it. It took him a while to actually convince himself that there was something to it. I will make few comments about this. So first he didn't like it, then he loved it. The reason he loved it because actually this very idea was used later on in formulating his general theory of relativity. So what is this about? It is essentially about the fact that space and time have to be treated equally on the same footing. And in addition, the metric which describes this space, the space is flat in special theory of relativity, and the metric which describes in Cartesian coordinates, you see it there, the metric is invariant with respect to all rotations, boosts, the Lorentz transformation is invariant, and that's what is the Poincare group about, where L stands for the Lorentz group of rotations and boosts, and T3 plus 1 are translations in time and in space. This also will become a little bit important, a little bit later. Now, so that's the essence of special theory of relativity. And then Einstein, shortly after he published, practically at the time when it was published, Einstein started thinking how to first include accelerated coordinate system frames of references into his theory, and later on how to get gravity in it. And both are somehow related. So if you read some textbooks or books devoted to general theory of relativity, how it was created, the first thing you would see is that some authors portrayed this like Einstein was still in the patent office in Switzerland when suddenly he got this great idea. I will say what the idea was in a few minutes. And having this idea, he sat down, wrote equations, and that general relativity was born, which means essentially that pretty much being genius, it took him no effort to develop general theory of relativity. That's pretty much the picture most students get out of textbooks when you read textbooks devoted to general theory of relativity or popular books. Well, I would like to actually present a completely different view, telling you that for 10 years, day and night, Einstein worked very, very, very hard. I hope all students hear me. Yeah, and he was genius, okay? He was genius. And he worked day and night, every day and every night, trying to develop this theory. So this was not 1 second effort. I take you through some steps so you see what it actually took. First of all, this picture implies that he had to modify either special theory of relativity or do some major modification and changes in order to develop general theory of relativity, which was essentially about gravity, how to correctly describe gravitational field. Here's Einstein's effort to account for gravity. And just please take a look. 1907, remember he published in 1905. He already did bending of light and some homogeneous gravitational field. Then he did accelerated frames in space-time, static gravitational fields. Then there was a very fundamental paper by Einstein and Grossman in which he finally learned mathematics to do this, his theory. He had ideas about the physics which underlines gravity, how he wanted to present gravity. He had no clue how to describe this mathematically. It took him almost, since 1913, it took him a couple of years to learn very hard mathematics, which was needed to actually do these formulations. Then there was this drama between Hilbert and Einstein, which happened just exactly 100 years ago, and I wanted to also emphasize this. So let's just move on. First, the paper in 1907, where he showed, sometimes I will just show only brief pictures, essentially making a point. Like in this case, he already had an idea that the space-time should be curved in order to account for force like gravity. That was his original idea. And then in 1907, he already predicted, it was not fully correct, but nevertheless, he made a prediction of bending of light. He also had this wonderful idea at that time, around 1906 or so, saying that once you are in the free fall in gravitational field, you actually do not feel gravitational field until you hit the floor. Otherwise, you do not. So that was his idea, and this idea got implemented later in his general theory of relativity in a very strong way. It plays a fundamental role. So here's what happened. Einstein had all these ideas in his mind, in his brain, and he knew pretty much what is physics behind gravitational field, how to describe gravitational field using curvature of space-time. However, he had no mathematics that would be the right mathematics to write equations of motions or equations of how to calculate, how to determine the curvature of the space-time. He didn't have mathematics. He talked to his professor, Grossman, who was a mathematician, and when he explained to Grossman his idea about curving space-time, Grossman says, I know what you are talking about. And he said, you do? And he said, yes, I do. The reason is because he was familiar with the work of Riemann, which was done half century early. And work of Riemann was essentially along the same lines, except that Riemann was a mathematician. And what he did, he wrote exactly what you see here, which means he formulated what are manifolds, how manifolds are defined, and how you define in one unique way a curvature of the manifold. So actually Riemann went one step further, believe it or not. At that time, in the middle of 19th century, he tried to explain forces known to physics in terms of curvature. So that's how far Riemann went. When Einstein read about this, he said, but what are those symbols? And Grossman said, those symbols are tensors. And said, I've never seen this in my life. So he started. On the same night, he basically took all the books which were on tensor analysis, went home and started reading them. He didn't know anything about tensor analysis. So that is actually an interesting thing to know. So what is a manifold? Is a smooth, continuous object, mathematical object, which has such properties that if you look locally at it, it will have, like in this particular case, a Euclidean structure, meaning that very, very locally, you could consider this to be flat at a point. But if you look at the whole manifold, you would see the curvature of the manifold. So this is obviously, from mathematical point of view, it shows how you define all those different functions and bijections in order to go from the manifold to the real numbers from the manifold to a plane, and so on and so on. Now, at each point, you can introduce a tangent space. And in this tangent space, you can obviously define certain physical quantities there, like velocity and things like this. So that's what Einstein started learning. And as I said, it took him 2 years, actually, to understand these things and start developing his own mathematical tools to formulate general theory of relativity. Now, so what is the mathematical model of space-time originally presented by, I should not say by Riemann, because Riemann didn't use the concept of space-time, but Einstein and Grossman in their paper 1913, they actually did use it. What is here the most important point is the metric that you see, ds square. This ds square is the, you see, metric tensor, which is the g mu nu, and that's pretty much the ds square is the measurement between two different events in space-time, which is uniquely determined once you know what is g. And g changes from point to point, from event to event, because space is not flat, space is curved. So this g will describe what kind of curvature the space has. So there's if you have a freely falling object in this manifold, it will follow timeline geodesic. Geodesics are shortest distance lines in a given manifold. So some of these concepts, like the definition of the metric, come actually originally from Riemann. That's the reason those manifolds are called Riemannian or pseudo-Riemannian. I will make a distinction. We will pretty much talk about pseudo-Riemannian. Pseudo-Riemannian is the one which, instead of having a Euclidean, locally Euclidean space, it has Minkowski spacetime, the one we just discussed a few minutes ago. So Einstein was extremely happy once he learned this. Why? Because here was the tool. The tool was given to him, how to define one unique way, how to determine metric, how to define uniquely a manifold, and it worked with his idea. In which sense? It worked with his idea because locally it could be Minkowski, which means, remember that idea that he had when he was still a clerk in the patent office. His idea was that in a free fall, you actually are locally not affected by gravity. So you could have inertial frame of references, those from special theory of relativity, at every local point that you pick. And this would work very well. So the model which was presented to him mathematically was actually a correct model which fit very well with his physical ideas. His physical ideas were this, that gravity is described by curvature of space-time. And the only thing what you need to know to determine a gravitational field of any strength is to determine one unique way how to calculate the metric tensor. Once you know the metric tensor, the little g, then you know ds. Once you know ds, you know the space, time in which you live, in which things happen. Does this all make sense to our graduate and undergraduate students, what I said so far? Are you guys with me? So I can go on with this right pace?
Yes. Okay.
Okay, so let's move on then to the next step.
Can I just make a comment?
Yeah, you can make comment anytime.
Okay. About if you can go back to the previous slide.
Sure.
I think just a brief comment about what I want to say about the geodesic work was actually motivated by geography, by mapping. So people at that time tried to produce good maps which could be used for different purposes, and so you need to have take into account that Earth is not flat but round. That was, at least the way I understand it, at least feel free to correct me, I think one of the drivers.
Yeah, that was right. That was originally, they did it for the sphere, for the globe, right? Once we figured out that we live on the globe, then that was natural thing to look for the shortest distances on the globe. Anyway, so here's the drama. Here's what happened. Everybody's ready for that? Don't get too nervous. Okay, here's what happened. Maybe just a little introduction to the drama. First, it was June 1915. No, it was May 1915 when Hilbert, very famous German mathematician, invited Einstein to his house to stay with him and deliver for 6 weeks lectures at Göttingen University, which at the time was like a prominent university in mathematics, right? Very well known, world-known place in mathematics with Hilbert and a bunch of other very good mathematicians there. And Einstein obviously agreed, and within 6 weeks, he delivered those lectures, and in the evening, drinking beer with Hilbert, they talk a lot about gravity and gravitational field and the ideas Einstein had. Apparently, beer and discussions helped Hilbert to understand the problem so well that he wrote his own paper on gravity. And in this paper that he wrote, he actually submitted paper on November the 20th, in which he presented the same equations that are now known as Einstein field equations. Hilbert actually did even more, one step more. He wrote a Lagrangian for those equations, and Einstein was still scratching his head what Lagrangian was about, because he didn't know those things at the time. He was just extremely good physicist, and I hate seeing Einstein on the first papers of Encyclopedia of Mathematica claiming that he was one of the top mathematicians who ever lived. No, wrong. He didn't know mathematics. He just knew physics extremely well, but people had to teach him mathematics. He had no clue. He never proved any theorem in his life. That's how good mathematician he was. But anyway, but this doesn't take anything away from him, because most physicists don't prove theorems, and yet they are good physicists. Anyway, so what happened was this. Hilbert wrote his own paper. Einstein left, went to Berlin, where he was located at the time, and he was actually putting 4 papers together on the same topic, but he didn't know about what was the development taking place in Göttingen with Hilbert. And apparently Hilbert submitted a paper in which he presented what is now known as Einstein field equations on November the 20th, 5 days before Einstein submitted 4 of his papers on November 25th to the Berlin Academy of Sciences. So I guess the equation should be called how? Hilbert-Einstein equations, right? Yeah. Then why in the world, in all textbooks, the equations are called Einstein field equations? Because of really a very strange development. One of the strangest in history of science. What happened was this. Both submitted papers to journals. And I don't know what kind of times those were, because those were not the times that we live, obviously, in. Because if Hilbert submitted his paper to journal on November the 20th, the paper was accepted for publication, and proofs were sent to him on December the 6th. I just cannot imagine that. But now listen to this. Einstein submitted on 25th, and the proofs were sent to him on the 2nd. What does this tell you? That we live in strange times. Those of us who wants to publish papers, and you send the paper, and for 3 months you hear nothing. Anyway, Professor Megron, go ahead.
I was wondering, did they submit to the same journal?
No. One submitted to this Berlin Academy of Sciences, the other one to Göttingen Academy of Sciences. Those were not like major journals. Nevertheless, very important work was published in this. So what does all this mean at the end of the day? Well, it means the following, that Einstein paper was still published because the proofs were approved by him and sent it back, was published a couple of days ahead of the formal date of publishing by Hilbert. Okay, and here is another part of the story, which is very interesting part. Einstein never mentioned Hilbert in his paper or anywhere, nothing, period, zero, nothing. Hilbert, in first original version of his paper, never mentioned Einstein. Pretty cool, right? But Hilbert finally scratched his head, and when the proofs came, he added a note saying that actually he got this idea directly from Einstein. So finally something clicked. And after that, I don't know who came to whom to see. I think Hilbert was invited to. Einstein had very bad feelings about that, okay? The fact that all these things happened. But then Hilbert came to Berlin, he was invited by Planck, and I think they finally went for good German beer and they finally cleared everything up and became friends. So apparently what convinced Einstein to become, it was very hard to become friends with Einstein, especially if you didn't write things the way he wanted. So apparently the statement that Hilbert added there convinced him that they should be friends. So from that on, now they had been friends, for all the remaining years. As you see from these pictures, I tried to pick the time when these things happened. Hilbert was approximately 20 years older and very well known, very well established mathematician, and Einstein was still on his way up. So that was also another thing. But anyway, so that was the little drama, which eventually ended up with Einstein having his paper published actually a couple of days early than Hilbert's paper. And Hilbert did not insist that equations should be called Hilbert-Einstein equations, or even Einstein-Hilbert equations. I think everybody else probably would insist on that, because having your name there would be a major thing.
But actually, the scientific community could still do so.
No, but they don't do it. However, they do call Hilbert-Einstein action, which leads to those equations. And this is a standard thing right now in textbooks, right? So Hilbert is there somewhere, okay? Anyway, so now, what I would like to show you is how Einstein wrote those equations. Finally, he learned tensors. He was a smart guy. He figured this out, that the tensors were extremely useful. I'm looking at graduate and undergraduate students and want to make sure that you guys do not ignore tensors. Tensors become very important in certain areas of physics. If you want to actually study general relativity, you have to do tensors. Here's one tensor that Einstein was extremely familiar with. It's an energy momentum tensor. He is written for perfect fluid, but that's beside the point. What he knew that in order to account correctly for distribution of matter in space-time, which actually is the main source of curvature of the space-time, you have to have the correct energy momentum tensor. And this energy momentum tensor cannot be higher rank than second order tensor. It has to be second order tensor. He knew that. So the question was this. He knew how to describe distribution of matter. However, he was not so sure how to describe the left-hand side, which was supposed to determine the resulting structure of the space-time. So here is a sequence of steps which were taken by Einstein over the couple of years to develop his general theory of relativity equations. Step number one, he took directly the metric tensor, gravity is on the left-hand side, the curvature of the space-time, the geometry of the space-time is on the left-hand side. On the right-hand side, where you see T, is the energy momentum tensor, meaning distribution of matter. So his first approach was, hey, let me just take G. But then there's a first fundamental problem, because if you take the derivative of the left-hand side and right-hand side, it has to be conservation of energy if you take the covariant derivative of that energy momentum tensor. But if you take covariant derivative of G, this is not zero. So he said this would not work. Then he moved on to use what is called Ricci's tensor. You may look at the Ricci's tensor. Ricci's tensor is here, this R mu nu. And why Einstein struggled so much? Well, the reason he struggled so much, because he knew the right-hand side of his equation, but he didn't know the left-hand side. He didn't know which tensor he should pick to correctly get his equations right on the left-hand side. Why is that? Well, Riemann, originally in his original work, actually showed and proved that the full curvature is uniquely determined only once you know what it's called a Riemann tensor. And Riemann tensor is this tensor here, when you see there with this 4 superscripts there, sigma, mu, nu, and rho, that's Riemann tensor. So it's 4-rank tensor. So that's the tensor which you actually should include in your equations. And Einstein said, but you cannot have on the left-hand side 4-rank tensor, on the right-hand side 2-rank tensor, because that every mathematician will say to you, just go away. I mean, you don't know what you are doing. You cannot do that. So that's it. Pretty much this stopped Einstein from, he had to figure out what to do. So he picked R mu nu, which is the Ricci's tensor, right? You see, it's a contraction of Riemann tensor. And again, the conservation laws didn't work, didn't come up naturally. Or another problem that he sometimes had was the fact that he could not get the right weak field limit, which he wanted to be gravitational field described by Newton. So essentially, those were like having the Poisson equation, which would describe correctly, based on gravitational potential, the gravitational field in the limit of weak fields. So you see it here, what happened, that Einstein had to add one extra term, 1/2 R, G mu nu, that R is Ricci scalar. And finally, when he added this one term, the left-hand side and the right-hand side conserved the right-hand side, the energy, which means that was the right set of tensors, which would satisfy also conservation of energy. So Einstein took at least 3 steps. I'm simplifying these things a little bit. At least 3 steps to develop his equations. And fortunately, all of this happened right timing, because if he was a little bit slower in that, Hilbert probably would have published more papers, and the theory would be known as a Hilbert theory of gravity. So as you see, this is the full glory Einstein general relativity, Einstein field equations for general theory of relativity. And what you see here is that this is called Einstein tensor. And this is really the only one contribution by Einstein to tensor analysis, when you clearly see his name saying Einstein tensor. Nothing else. All other tensors that are known by names have nothing to do with Einstein. So now we have the Einstein field equations. And obviously the first question is, well, those were new equations, and Einstein was first who tried to solve them. That was very natural way, because he wanted to predict certain phenomena which were known. Like the first thing that he tried to account for was the fact that it was known in astronomy, discrepancy between the Mercury's orbit and the prediction from Newton's theory, and Einstein calculated this using general theory of relativity, and he immediately found a much, much better agreement, actually almost perfect agreement with observational results by astronomers. Anyway, this is the original paper. Einstein wrote the paper in March, I believe, 1916, and the paper was published in 1916 in German originally. And the paper is the full foundation of general theory of relativity, which includes this prediction for Mercury. Now, Einstein put a lot of emphasis to something which is no general covariance. Means he wanted to write equations. The equations of physics should be written in such a way that they are independent completely and totally from coordinate systems. He put a lot of emphasis. This is called principle of general covariance. And for years, he had been criticized by this by all different physicists. He responded to some of them, those papers which were written after he passed away. Obviously, he couldn't respond, but I don't think he didn't care too much about them. Anyway, because the fact is that Einstein had his own beliefs, and in case people were writing papers and criticizing him, he just basically played his violin and just kind of ignored those things. Now, mathematicians also got to this. And this is actually an interesting, it's a part of math. Here, mathematicians use diffeomorphism and a special type of mapping between manifolds. And the main point of all this is essentially to get a special diffeomorphism transformations. So this is like, you see here, I don't have a pointer, but you see here when x goes to x prime, forms a group of general coordinate transformation. That's this diff m. And the problem is with this, that the group does exist, but it doesn't have physically acceptable irreducible representations, which means the group actually doesn't have the same meaning as Poincaré group has, for example, for special theory of relativity. So GR is invariant after these transformations, but what does it mean physically? There's no, strictly speaking, group with irreducible representations that could be used and justify mathematically and physically this particular diffeomorphism. When Einstein read all those things, here's what he had to say. He said basically that since mathematicians started playing with that, he had no clue what general theory of relativity was anymore. And I think he got the point. Okay, so here's all, I try to summarize on one slide what general theory of relativity, the fact that it's the best theory of gravity that we have. There are some other theories which were developed over the years, but they do not match. They always have problems one way or the other. GR is our best theory of gravity. It makes predictions. It changed completely astronomy. It changed completely our view of the universe. It changed. I could just only talk for the next 30 minutes what it did change. Here's the summary, very brief points, only highlights. It's global structure and evolution of the universe, right? The Big Bang, the origin of the universe. This also comes existence and structure of black holes, bending of light, gravitational waves, and so on and so on. Now, there are some limitations. And one of the limitations is that it describes only point particles and large masses. It's classical theory. Another limitation is that it does not account for quantum effects at all, predicts singularities, which are real limits of validity of the theory, like you see here, a black hole, and you see the beginning of the universe. Now, so what I intend to do right now is go relatively briefly, but I really do like to present to you at least two types of applications of. Oh, thank you so much. Oh, that would help if I press the right button. Okay, thank you. It doesn't work.
Put it on.
It's what?
You have to turn it on first.
Slide it
Oh, really? Oh, come on. You gave me without turning this on.
It's on the side.
Shut up. It's here?
On the side.
Yeah, I'm trying, but there are two sides. It may take me 10 minutes. Come on.
The six sides.
No, I would never figure that out. Okay, don't be too hard on me, okay? I'm talking about black holes, and finally you give me something like this. Anyway, so the point is this. I would like to just, first, what I would like to say is that black holes, maybe I should move to the next one and show you, no, this doesn't work. It's okay, I will do it here. First black hole solution was found by Karl Schwarzschild in 1960, who was actually a German soldier fighting Russians during the First World War. And basically, at that time, he had enough time between the shots to solve Einstein equations. And it seems to be working extremely well because this is the best known solution to Einstein equations ever published. That's Karl Schwarzschild. He unfortunately didn't live long enough. He died premature from some very strange disease, not actually from Russian bullets, but from some very strange skin disease. Anyway, what I want to say is that Schwarzschild solved Einstein equations, as I say, being a soldier. Essentially, what it boils down solving Einstein equation is the following. You see that metric there, ds, with two parameters, a as a function of t and b as a function of t. In general, they could be also a function of r as well. But in general, okay? But nevertheless, what you are supposed to do is use this metric, put this metric in or use the spherical symmetry that you have here and write Einstein equation in spherical symmetry and solve them for these two parameters A and B. Once you do this right, how long is the algebra? Typically it's 20 full pages of calculations in order to get what you see here. So what do we get? We get actually an interesting result. We get a metric where this term becomes term which looks like this. Rs is, if I'm using natural units, is just the mass of the central object. And this is another term which looks like this, but it's actually 1 over. So here's what happens. When R sub s becomes equal to R, you do have a certain type of singularity here because this becomes 0, or this goes away completely altogether. So also you have another type of singularity when R approaches 0, then this all blows up. So you see that black hole does have a certain type of singularities. And that was the first implication of Schwarzschild solutions. When he sent this to Einstein, Einstein said nonsense. That was obviously his first approach. And he said nonsense because something like this will never ever exist in any universe, especially in our universe. So that was his first approach. But he was obviously wrong because it took astronomers a long time to discover, but yet we know a bunch of black holes these days. And black holes are very well known. So now, another point here is that are these singularities truly physical singularities, or these are only mathematical problems with particular set of coordinate systems we are choosing? And actually it happens to be the second, because there are two different types of metrics. One is classical metric, one is Eddington-Finkelstein metric, which actually allow you to remove singularity at R equals Rs. However, nobody can remove singularity at R equals 0. So Schwarzschild metric is known, very well known in general relativity studies. And Schwarzschild metric is the one which was the first original prediction of the existence of a black hole. So very briefly, right, just very briefly, because I know that some of you are familiar with it. So essentially, this is the central singularity, and this is the so-called even horizon singularity, where R equals R sub s. That's how it looks. It's like a sphere around the central singularity. Once we enter this this even horizon, that's where all the lights get trapped, because the escape velocity is is larger, higher than the speed of light. So what happens? Actually, there are interesting things that I want to show you, because if I get there, I may have to use this again to show you that actually, if you get, what happens when you get very close to the event horizon? Oh, the gravitational forces are so strong that actually light, there are certain orbits on which light is confined to travel along the orbit. So if a person is located there, like this lady who is located there, she would see her face and her back at the same time, because photons are confined to that particular orbit. So you can do comb the hair in the back and the front, and you don't need any mirrors or anything. That's one thing. Second thing is what happens when you are entering the black hole. This is a long story. There's a lot of literature on this, written on that these days. Things become very interesting because people call it spaghettification, when the pull on the feet is much, much stronger than on the head, and the person gets 1 mile long before it enters the event horizon. You see all arrows point towards the center. So what does it mean? That eventually, whether you like it or not, you will end up here at the singularity. That's something that the black hole does. The central singularity also forces the light cones to change. This is light cone far, far away with time and space. Look how things change once you cross this one, which is the event horizon singularity, and then everything points towards the central. The future always points towards the central singularity. That singularity is the point at which Einstein's general theory of relativity breaks down in pieces. So singularity here is, just shown pretty much as here's the event horizon, and the singularity here is shown like a point where all the mass is located, and where everything, all the density, all the physical, non-physical parameters reach infinite values, which mean the general theory of relativity, cannot make any predictions what happens near vicinity of the singularity. Now, the question whether this is this known, or do we know black holes? Yes, we know black holes pretty much. Astronomers discover all different type of black holes which are as small as stars surrounded by accretion disk, mid-mass black holes, and supermassive black holes at center of galaxies. Now you talk to astronomers and they will give you the whole spectrum of black holes, something that Einstein wrote the paper in 1939 saying that he doesn't believe in any black holes. Well, 30 years later, we already discovered first black holes. So you see, even people like Einstein actually had hard time to accept certain predictions coming out of his own equations. So what I would say is, just to summarize this in one sentence, is that probably equations that Einstein developed were smarter than Einstein. Because there are certain predictions were coming out of these equations, and that's pretty much what. Now, about cosmology, general relativity and cosmology. This was another topic. Yes, Suman, anytime.
Yeah. So the volume is zero in the singularity.
It's what? Say.
Volume is the volume. Volume is zero in the singularity, and you have the infinite density.
Yeah. Right. Well, the point is the point. Singularity is the point.
No.
Right. So with the infinite value of density, with the infinite value, right? That's pretty much what you know based on the theory, right? This is what you know. Now, as we all know, Einstein did make a mistake. One of his first calculations were applying to the whole universe his theory, and unfortunately, he believed that the universe is steady, and he introduced this factor here, which is known as a cosmological constant. He got very nice steady solutions, but those solutions were wrong solutions, right? Apparently, they were wrong solutions because eventually, as we know, the universe is actually expanding. And the credit goes to Friedman, Russian mathematician, who was the first who actually predicted that if you take the A to be the radius of the universe, you will have three different solutions depending on the global curvature, whether the solution will be, linearly expanding or close, or it would be expanding more kind of flat, but still expanding along this way. So he is credited with making, in 1922, he made a prediction of the expanding universe. And this is the Robertson-Walker metric. Now we are more familiar with metric where this capital R here stands for this little r. They are basically related to each other. And this r, which is the radius of the universe, is related directly to Hubble constant. And you have three different types of solutions which come naturally out of the Robertson-Walker metric. This work was done after Friedman already passed away by Robertson and Walker in late 30s, and it's a very well-known work right now. It's a standard cosmological work, meaning that this is the standard what we know about cosmology, and that's how it leads to Big Bang and all the things that we currently know. These are the actual models, depending also on the amount of matter and amount of also dark matter and dark energy are kind of included or must be included in it. So you have accelerating open universe, open low density, flat, close, and so on. These are, as I said, standard taken from textbook solutions. Now, one historical point that I would like to pointing out is that Lemaitre, the French Belgium actually priest, was in 1990, he was 3 years ahead of Friedman, and he showed under some circumstances the space can actually expand. But his universe was universe without matter, with cosmological constant. And but nevertheless, he was one of the first who talked about space expanding. So some credit should probably go to him. Now, Hubble obviously produced his diagram, which changed completely the astronomy, and we are familiar with it, right? Is the linear increase when you plot velocity of galaxies moving, or cluster of galaxies moving away from us with distance to those galaxies, then you have a linear dependence. And this linear dependence, as you know lately, within the last 20 years or so, has actually been shown that it is actually not completely the way we originally thought that it would continue, but instead, it is more, the fitting goes better in the region which corresponds to accelerating universe. And that's what is known and caused as, that's for what Nobel Prize was awarded, when two teams show independently that this leads to actually accelerating universe. And then this accelerating universe, as you see here, up to a certain point, it was actually slowing down, and then the expansion started speeding up. And those further supernovae were somewhere measured here and in between. So this all has enormous implications, because we pretty much know right now that most of the important part of the universe, which is dark energy and dark matter, we really do not know what it is. Anyway, so let's go back to Einstein's general theory of relativity. People are trying to use it actually to determine, to say what, for example, how to explain dark energy using cosmological constant. Here is cosmological constant lambda, right? And people try to use actually this lambda as a quantum, calculate lambda from quantum field theory, vacuum energy densities. And the numbers that you get, QFT predictions, if you add SUSY, the number goes down, but 55 as compared to be 10 to the minus 29, it is a very strong fine-tuning, which doesn't go anywhere. Nobody knows how to calculate lambda correctly. People came up with different ideas. This is again Einstein general theory of relativity equation. And what you see here a term which shows how gravity is weakening on the large scales. People try that. Guess what? It doesn't work. So what is working? First, what are theoretical challenges? The way I see them. So the first question is, are those singularities that we see inside black holes, are singularities that we see at the Big Bang singularity, are they real or just mathematical artifacts? Is going to happen that one day somebody like Kraskell and others, people for years believed that even horizon singularity was the real one, but actually it wasn't. So Kraskell showed that it was not. So maybe one day somebody will look at this and say, "Oh, you all made mistake. That's the way it should be, and there's no singularity." But I don't think so. I think this problem will be persistent problem there until we really combine general relativity and quantum field theory. And the question is whether such quantum gravity would solve the problems or not. It remains to be seen. Now, there's also other trend these days in theoretical research is to identify potential areas where general relativity could fail, could break down. And that's what people are also working very hard on. Now, from the experimental point of view, one thing that I want to say as loud as I can, is that there's no observational, astronomical, any evidence which cannot be explained by general theory of relativity. General theory of relativity explain all the things that it's supposed to explain, period. The same with the gravity-related physical experiments performed very precise studies at the University of Washington in Seattle, and everything seems to be consistent. It's on very small scale. These are not directly verifying general theory of relativity, but all other physical experiments which were performed, they confirm predictions of general theory of relativity. So there are a couple of things which astronomers identify. One, they want to take a look at a very, very near, very close to an even horizon of the black hole, and hoping that NASA would approve one of those missions, that we can measure X-rays practically at the even horizon. That would potentially give us some hint whether GR is violated there or not, whether it still describes physics correctly. Obviously, I'm not going to get into this about gravitational waves because you just heard the talk a couple of weeks ago. Well, we still don't see them. Now, so that's what pretty much what observers are trying to do. Now, I have like 5 minutes left, so let me just very quickly tell you a little bit about what we are trying to do here. We are doing work on general relativity, and to say that what we do is relevant to what I was trying to describe today is that we actually, our approach is different than anybody else in this particular business. The fact that we are doing work on a regular basis, I have a proof, because Dr. Nygren can, I hope, justify that. Seeing us there twice or three times a week, working extremely hard and arguing. From time to time, John Fry and I argue so loud that we have to close the door. But anyway, there are a couple more people involved in it, and Gordon Cannon is our graduate student who is working with us. So what we are trying to do, let me just very briefly tell you. We originally started with flat space-time, Minkowski metric, the one that you are familiar because we already talked about that. We use the invariant subgroup T3 plus 1 to actually show that this group requires that there is an eigenvalue equations of this type, and that we have those K's here are the labels for a fundamental wave. We call fundamental wave the wave which transform as the irreducible representation of the group of the metric, the Poincare group. This is Minkowski metric, and everything is very standard. And we actually worked pretty hard, John and I and a couple of our students, to prove that from those eigenvalue equations you can derive Klein-Gordon equation, Dirac equation, and we also know how to do it for Proca equation. We probably could do it for tensor spinors, wave functions, and others. This was all published in a bunch of papers. Just to tell you that we actually have done quite a lot of work here. But now what we are after is what happens to those fundamental waves. Our fundamental waves are very important to us in the following sense. These are the waves which become fundamental, the same for all observers. Means doesn't matter who is the observer, will identify this wave. But the space-time this time is not flat, it's curved. Being curved, we have to change. We cannot use that eigenvalue equation we did before. So we introduce a new eigenvalue equation, which are local eigenvalue equations. You see it for Q here. This Q is a local quantity, right? It's not like before it was K, which was the fixed number. So we have a scalar wave, and scalar wave function can, for example, describe boson, Higgs boson. Now, we can write the energy momentum tensor and solve Einstein equation. This is a long process. It takes pages to do that, even in Cartesian coordinate. What you immediately discover is if you do that, the number of solutions which are resulting solutions out of this, but one of them is a very interesting solution here that you see the time actually will appear here, which means things will go exponentially in time and grow up. This is the space will actually expand in time as a presence of scalar field, something like Higgs. This is a new thing which potentially could lead to some new view on dark energy. And now, I'm almost done, so I will try to finish at 5 with the speed of light. What we did very recently, we just look at the black hole solution, and we did the fundamental wave. So here's the setting. We have a black hole, which is a central mass, and pretty much space far away, it's empty space. There's nothing except the central mass. And then what we did, we solved, first we wrote down the energy momentum tensor, and then we wrote down the general metric, and we solved for those A's and B's. As again, it's a long process. It's hard to find solutions because the resulting equations are nonlinear, but nevertheless, we found the solutions. And what did we find? Instead of showing you, what I should do right now is show you 20 pages of mathematics, and I know that nobody's ready for that. So what I'm going to do instead, show you a couple of pictures that you are already familiar with. Okay, pictures that you've seen in this talk. And I will tell you what is our prediction. And my coworker is sitting there, so he's watching me. And if I say something wrong, I know what he's going to say. Are we familiar with this? Yeah, what is this? It's the Schwarzschild solution, right? So how our solutions differs from Schwarzschild solution? Maybe I should let Dr. Fry to say it. It differs in the following sense, that we are adding something. We found something, our wave, scalar wave, Higgs, which sits there in the whole manifold with the black hole. It actually adds a skin, very tiny, narrow skin to this event horizon. So there's actually a very tiny skin here. So what we have so far found is that black hole can have a skin. Now, the next step would be to let that skin grow higher and say that. And why am I saying that? Oh, because there's a theorem. classical theorem which says that black holes cannot have hair, proved by Hawking and proved by Penrose. What does this mean? It means that if we can grow hair, you see, our wave is fundamental wave. Our approach is different approach. Essentially, what I am saying is this, that where this lady is there, is that she could be within that skin. And that's where the light is trapped. That's where she doesn't need a mirror to see the bed. And that's where all the interesting things are happening. Why this is important and critical? Because if NASA approves the way the observers want to look at it, means they want to get X-rays just exactly, remember what I just said a couple of minutes ago? Exactly at the event horizon. That's where they want to get the X-rays from. So if we are right, then we have black hole with a skin. Don't tell anybody because nobody knows about those things, okay? Yet, the paper has not yet been published, right, John? We are still thinking about this. But the bottom line is that that's the main result.
How thick is the skin?
Well, this depends on what kind of mass of the particle we put. If we use mass of Higgs of our friends who found Higgs at CERN, then we can tell you that it will be relatively narrow, right, John? Very, very small, very tiny, narrow skin around that black hole. But nevertheless, what is interesting about that skin is that once you approach it, the metric is completely different. I don't have time to get into this. The metric changes drastically. What is on that side at the skin, and then what happens at the event horizon. So,
A skin of what exactly?
the skin means there's a region in which physics is different.
Okay.
That's what I call skin.
Okay.
Right? And as I said, growing hair means allowing things to communicate with the world outside. That's what I meant by growing hair. I'm sorry that I am using kind of jargon, but
It made the term
Jordan, yeah.
Thought when I had skin, it made it sound like it was like composed of something.
Right. So I am assuming that the best way to finish my talk would be just to show pictures of Einstein, because that was, after all, tribute to Einstein and his theory. And all what I wanted to say here is how great this theory is. I do not put much emphasis on what we have done, but it kind of fits nicely within what I wanted to say. However, if Einstein were around, if he were around, I'm sure that he would ask, hey, so what is really next? What has to be done? And I think truly what has to be done next is to push more in that direction, trying to describe different quantum phenomena on one side and general relativity on the other side, and see whether this matching leads to some new physics and some new development, like that skin that we just discovered. So I really would like to thank you very much for your attention and for staying with me in this tribute to Einstein. Thank you so much.
Any questions?
Okay, so Polchinski gave some popular article about a firewall, so to speak, at the same event horizon. Any comment?
Yeah. Well, it's a different approach completely than what we are doing. It has nothing really to do with our approach. It's more like waving hands in this case. I'm sorry to say, he's Polish, I know him. But, but it's a little bit more like waving hands, okay? What I mean by this is that people we are doing, what we are trying to do, Professor Nygren, is to put everything in a very self-consistent way based on the most fundamental principles which were used to develop theories. What they do, they means others, what others typically did was essentially to write a certain equation and find solutions. And then if they say, oh, well, wait a minute, maybe I need to add some curvature term to it. without really justification or saying, where does this come from? You don't ask those questions.
Thank you.
I mean, that's pretty much what they would tell you if you would say, right? Like those guys, because they say, well, everybody does this. You know, when I asked that question at the conference, the answer was, well, everybody does that.
Hmm?
I don't. But anyway,
Good, thank you.
sure.
I have two questions. So, what does your skin do to Colloquium's considerations of information transfer?
That is actually an excellent question because the skin may increase that, may say something, right? That normally you would not know without the skin. But on the other hand, it may block, and it may block actually the even more communication because it has different metric. And what we didn't know really, what we were just talking about is yesterday, how this new metric, which described the skin, may block the information from getting towards us or outside of us. But you see, the wave, that fundamental wave, what is good about this and nice about it is the wave which is everywhere. It reaches even singularity. And we were hoping that by studying that wave where we are far away, safe, away from the black hole, we can say something what happens inside the black hole because the wave may react, right? I mean, that was the idea. Since it's fundamental, remember, it has certain very strict properties, right? Yeah.
So, we've been searching for some time for evidence of extra dimensions. How would that affect geology? I mean, it's developed in a limited number of dimensions.
Well, I think it would, especially if you would add actually the fifth dimension to it, right? Well, that would be a different GR because GR is all what it is about the background of space-time, which is, curve. And remember, the theory, it's so different than other physics theories because it actually changes the background. Normally, when you develop the physical theory, is the theory which has the fixed background, like quantum field theory. The background is fixed. But not here. The background is not fixed. The background changes. You have to calculate what is the background before you do anything. So that's what is completely different thing about this, right?
I have a much more simple question. I read something recently in Pop Science about another calculation of the source boundaries where it was half as large as always.
Yeah, these things changes depending on mass of the inner mass of the object, right? So whenever you have bigger mass, it's bigger. When you have smaller mass, it's smaller.
So that's all that was. Is they just have
this is all what it is essentially at this point, right? The mass of the central mass is all what it determines where it is, how far it's located from the center. Yes, Manfred, go ahead.
Okay. Well, I just try to think about that skin concept and think about how to perhaps link it also to the Big Bang itself. So I've seen, I think, some ideas at the point that some scientists were thinking about time prior to time. So what happened prior to the Big Bang? Was there any idea to expand the theory?
Well, and this is
Bang?
yeah, I'm sorry. Yeah,
Yes.
go ahead.
I think I communicate. Yes.
Well, actually, yeah, this takes us to another point that we would like to explore. We haven't done this yet because we started playing with those black holes. But the basic idea was this. Can we penetrate singularity? Can we actually explore singularity by those fundamental waves? Can we say something, right? What happened actually at the Big Bang closer by, pure theory instead of measuring? I mean, high energy physicists, with all my respect to them, they could never get there. Never, ever. Because the Big Bang happened at the densities and energies that these guys would need all the money which is on the earth to produce their next generation of colliders to get a little bit closer, but still they cannot get. But our wave doesn't care about money or anything. It just can go there. The question is, doesn't give us any information when we are so far from it, which is the point, right? Yeah, right. And we still do not know the answer, but it's a very good question. That's where we want to go. But, so if you see one day that John Fry and I disappear, it means we went on the other side of the singularity. Right, John?
On that note, so
Yeah, the talk was supposed to be fun, right? Not just only very serious physics, right? Thank you, Andy. What?
Don't cross over for a while.
Justin, you I have a question. I think on one of your slides, I think it was freedom metric. I think there was a term that was dr over 1 minus kr squared.
Yeah.
So what happens when r takes on the value of 1 over the square root of k?
Well, actually cannot. K is fixed. It's 0, 1, or it's 0, negative, or positive.
So you can never get a singularity term.
You cannot get singularity of that type. Yeah, not for me.
I think it just took a second for it to download
the percentage
Sorry
of
about
Thank you so much for having me with this. Anyway, I switched this. I don't know what to do with this. Hello. Have I already left? I need to switch this off. No. Computer, I know how to switch.
So,
But,
design theory.
so would you switch completely off because I think I'm logged in?
So when they came here, they probably affected three forces from us. So right now, since the initial stage project,
We don't know
that's the
anything
percentage is
beyond
not high because the student
No.
But your skin is not adamant.
No, it is just above it.
Like,
Means like if you have sphere, this is just above the sphere. Like you would add something to the sphere.
Right, this is what I was thinking.
So all the
This is your
forces
event
is
horizon.
Yeah.
And this is your skin.
code
And
is
you already don't know anything about it.
Right.
Is it possible that our not knowing is due to that skin?
No, the skin
we
is
have-
actually by itself is a new phenomenon.
Right, it's a new physics.
Right.
So that's where the
Coincide,
physics
Yeah.
breaks
It
down.
is a new
Yeah, that's
phenomenon.
the thing I think.
So would that have any
Any
connection to dark matter, dark energy? Because I don't know.
I don't think so. Not at this point.
At least not even.
The first solution that I showed it could, but not this. Because this is strictly
like the
speaking
PS Pro system,
a
we
new
should put
phenomenon
our
for
faculty
a black hole.
So
Right?
maybe we can get half the credit.
It would not,
have
because we don't know what dark
Have
matter
the
is, we
research
just know that
credit.
it should be there to balance it out,
Oh,
right?
when they
That's all we know about dark
research,
matter.
I don't know.
So could it
I don't know.
possibly be that those
Then
are
they can
just
take
that
3
much
credits of
more
us
than
and
that?
6 credits
Yeah,
of them.
well, the dark matter, is a different.
Yeah, this is a thing.
So if
you,
the skin
need to
were
talk to
very
them.
big, and inside we know the matrix is terribly different from our normal.
Anyway, I'll
Terribly
I'll
different.
look at it.
It's not even related to physics. So like dark matter is inside.
Could be if the skin is
Okay,
big
too
enough.
close.
But can skin be that big? Right? That's
Well, it
another
just depends on the
on the mass.
parameters n over b.
Right. Well, thanks so much for all the questions. Did you go this way?
Yeah.
So, yeah. Actually, singularity means here that physical parameters, all physical parameters blow up. Means going to infinity, and that's it. That's what is singularity. So the Big Bang singularity obviously is more prominent in the sense that it's the origin of the universe behind it. But the black hole singularity is just
good.
general theory of relativity fails.
Yeah.
And it breaks down.
Although I
And you
emailed
don't
him and I got
know
a reply that he's out of town, but
it
email him
breaks down
anyway.
in both cases.
Maybe he'll come
The
back.
same way means it's infinite. You were sitting quietly.
Yeah.
We're doing the talking.
Yeah, but you could say something. So,
So these were equations that were experimentally derived and then empirically derived, basically, and then at Stanford, he kind of came up with. I mean, like his PhD advisor, he's got to create.
Did you sign that?
Oh, I didn't sign.
See? Whose laptop?
Yeah. Yeah, I just realized I forgot it.
Oh, whose laptop?